Hi everyone, welcome back. So today I'm going to be doing something a little bit different today. We are going to be using a tablet for this demonstration. And for today's demonstration we're going to be doing the Gaussian integral and going about how we're going to solve that. So let's get to it. Alright, so we have our Gaussian integral here, where our limits of integration are from negative infinity to positive infinity. And the integrand we're going to be integrating over is our exponential e raised to the negative x squared with respect to x. So this can be actually represented on a Cartesian coordinate plane here as this bell-shaped curve, which its domain extends from negative infinity to positive infinity, corresponding to our limits of integration. If you want more of a visual representation of what we're going to be integrating under. So looking over here, you might be thinking to yourself, why can't we just use some of our conventional integral rules, such as U substitution, integration by parts, something like that? Well, by all means, be my guest, go ahead and give that a shot, but I strongly urge you not to, because you will end up broken and alone, and that fleeting moment of happiness that you once thought you had is nothing more than an aftertaste by the end of it. So, with that in mind, I would strongly urge you to just watch this demonstration and know that that is not the way to solve it. There are no elementary means of solving this. We have to use some shifty mathematics here. So with that in mind, you could also maybe think, alright, well, what if I were to punch this into an integral calculator? And you can. And what pops out is just an error function. So that is not how we're going to be solving it. We're going to be, like I said, we're going to be using some tricky little mathematics here to sort of trick the equation into thinking it has some sort of identity crisis, right? Which is my favorite. So what we want to do first is assign a variable here. We're going to call this g. That is not a pen. So we're going to call this g, right? For Gauss, right? So what we need to do here is basically make this more complicated, which seems a little counterintuitive, but if there's one thing I learned in mathematics, that things got to get complicated before they get easier. So what I suggest that we do here is multiply this equation, this integral, by another form of itself with a different independent variable, and I suggest that we choose y. So instead of x, we're just going to have y, and now we're going to have a double integral here. So let's do that. So our integral from negative infinity to infinity, and like I said, we're going to have a double here, negative infinity to infinity, and since we are multiplying it by just another independent variable of the same equation, we're going to use the exponent rule here. So that's going to give us e, factoring out the negative, x squared plus y squared with respect to dx, dy, and those can be in any order you want. It doesn't really matter. So at this point, let's actually just pull that y out here, right? Let's factor the y variable term out, because it's the constant, since that would be the outer term, and pull that out of the inner integral here. Let's see what that gives us. So we're going to have some integral here from negative infinity to infinity. Oh, I didn't do what I said I was going to do. So we have e raised to the negative y squared with our inner integral with negative infinity to infinity, where we have e to the negative x squared dx. So let's parentheses this out here so we know that that is where we're going to be integrating first. So it doesn't seem like we really got very far here, does it? I mean, we essentially just ended up what we started with, just two different terms. This actually is incredibly helpful to us. Now, obviously, we know that this is just g, and this also is g. It's the same thing. We just have a different independent variable here to represent that that distinction between the other one. Now, what we've essentially just proven to ourselves is that we can actually convert this integral to polar. I mean, if you recall from polar conversions, x squared plus y squared is just equal to r squared as far as polar conversions go, because x is equal to r cosine of theta and y is equal to r sine of theta. So we can actually just change this to polar. So that actually is a nice little interesting step. So we're going to trick this integral into thinking that it is a polar equation. So let's do that. So we're going to have now triangle there. So we have to actually change our limits of integration here. Now, instead of negative infinity to infinity, we actually need to include the distance around a circle here, which is going to be 2 pi. So this is going to be from 0 to 2 pi. And our inner integral is going to be our r variable, which is just going to extend from 0 to infinity. 0 to infinity. Where we now have e to the negative r squared. And due to our Jacobian, which is something I can prove in another video maybe, but trust me, we have to include this separate variable here of r, where we have this with respect to dr d theta. Alright, so this, in fact, is much more manageable than it was before. We can actually use some of our more conventional rules of solving. So now we can actually use substitution and have it not leave us just broken and in tears. So let's do that. So now we're going to have u equal to r squared, right? And then we're going to differentiate that with respect to r. So we're going to have du is equal to 2r dr. And let's move that 2 over, divide it rather. So we're going to have this become r dr equal to 1/2 du. Okay, so this is actually really great. So we can actually plug this all in now, and let's see what that looks like. So we're going to have this going from 0 to 2 pi, and considering that 1/2, when we plug it in, it's just going to be a constant. I'm just going to pull that out of the integral now. So we're going to have 1/2, and our integral from 0 to infinity. And generally, you want to change your limits of integration to keep things, fluid. However, this is going to be the same as this one is, because you just plug infinity squared, that's going to be infinity, 0 squared is 0. So not really anything changes, which is nice. So we're going to have that e raised to the negative u, right? And then we have du d theta. Okay, so now we can actually integrate this. So let's do that. So taking the indefinite integral here is going to give us, so just isolating this first here, ignoring the outer, of course, we're going to have 0 to infinity, bracketed off here, and then that negative falls down to the coefficient, so e raised to the negative u, and now we can actually take the difference here from our limits. So we're going to have, so this is the same as negative 1 over e to the u. And if we plug in infinity for u, we're just going to get 0. And negative 0 is still 0, so we have 0 here. 0 minus, and since, remember, there's a negative here, and a minus minus, and e, or 1 over e to the 0 is just 1. So this is going to be minus minus 1. We're going to have that there, which is just 1. Alright, so now, this, knowing this is just 1, we can basically just integrate over from 0 to 2 pi now, because it's just gonna be the same since we're multiplying by 1. So using that, we're gonna have our integral from 0 to 2 pi of 1/2. So we can factor that 1/2 out again. It's just another constant of d theta. So taking that indefinite integral is just going to give us theta. Plugging in for theta, we're going to get 2 pi. And that is going to give us 2 pi over 2. Canceling that, we just get pi. Alright, that is not our answer, as much as it may feel like it is. So let's retrace our steps just a little bit to figure out how we can actually come to the correct answer here. This is very useful. So as we've already described, our g's here are the same. We just expressed two versions of the same integral in polar coordinates, and we already assigned a variable of g for this one. So it would seem that this is just g squared equal to pi. And solving for g, like we want to do, is just going to be g equal to the square root of pi. And that is our answer. So there we have it. Our Gaussian integral here is equal to the square root of pi. Alright, that's it. Thank you for watching.